Good. All right. Now, let's look at the other data set you guys collected, which was the number of times we had to flip until we saw each face one time. So in other words, you had to keep flipping until you saw at least one heads and tails. Remember this problem? This was the longer one. Because I think it was Trey, you went like tails, 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 heads eventually. And you're out here in this 12, I think. Either you or Michael, I forget who was out here.
I was a 9.
You were a 9, Michael was the 12. So at this was keep flipping the coin. Keep flipping the coin until you get heads and tails at least one time each. Now, sometimes it was over in 2 flips. As a matter of fact, most of the time it was over in 2 flips, yes? Because you flip one, and then you flip the other one, and then you're done. But then sometimes it took 3 flips, because sometimes you went heads, heads, tails, or tails, tails, heads. And then sometimes it took 4 flips, because you went heads, 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 tails, or tails, 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 heads. I mean, you saw back on the original spreadsheet with the randomized tails and heads, sometimes you get those strings of tails and heads. You guys just experienced some of those. Describe the shape of this distribution right here. What's that looking like?
Bell curve.
It's half a bell curve. I like that. If you drew it, if you went out this way, the other half. What does this look like? Something we just talked about recently.
Oh, it goes straight up.
Isn't it? Isn't it exponential?
Yeah, it is, because it goes...
Good. Now, tell me why you think it should be exponential. It looks like this one is about twice as big as this one. This one's about twice as big as this one. This one's about twice as big as this one. This one's about twice as big. Why? Why would they be twice, or why would they be half as big as they go left to right? Think about it.
Does it go down with the percentage?
It has to, doesn't it? Every time it takes us one more flip to get the job done, we're going to lose half the people. Because half of you are flipping heads and half of you are flipping tails. It gets harder and harder and harder to flip a bunch of tails in a row, because you shouldn't be getting a bunch of tails in a row. You should be getting heads and tails alternating on average over time. That doesn't mean that you can't get strings of tails in a row. We saw that, didn't we? Let's look back at it again in case you don't buy it. Here. Right? String of 5 tails. String of 6 heads. String of 6 heads, right? They exist. They just don't exist super prevalently. Here's another one. String of 6 heads right off the bat. 4, 5, actually 6 if you count it from around here. They exist. But what exists on average? That's what I'm looking for. I'm not looking for the goofy extreme cases. I'm looking for the average cases. So now my next question is, on average, based on our data, how many flips should it take on average? Let's do it. Let's analyze it with our statistics. And I'm going to keep these up here so we can refer back to them. Now here's one you don't probably want to do like we just tried to do over here with the tree diagram. Because think about how many branches your tree would have to have. At least 12. Because we had one case of 12 flips, right? And technically speaking, wouldn't the tree have to go off forever? Because just because we had somebody go to 12, wouldn't it be possible to have somebody go tails, 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 forever? I mean, it's possible, it's just not nice, likely or probable. I like both of those words, they mean the same thing, and they're both 100% correct. So technically speaking, you can stop at 12 like we did, because that was definitely an outlier data point. But let's figure it out. Let's figure out our weighted average. Because this again is a weighted average, yes? Actually, this is I think we probably want to use this chart right here. Now I used Excel to tell, I've got the average right here at 2.96. I want to make sure we can all get that. So here's the data we collect. You can ignore from 13 on. For some reason I had to go to 15. What we have to do is we have to set up our average number of flips. I'm going to erase this. All right. Average is an A then. Number of flips until we see heads and tails. At least once. The point is at least once. We didn't have to see this in the last experiment, because in the last experiment we could be done with heads and heads or tails and tails. So we have to figure out the numerator, which is going to be the sum of all the data. So technically speaking, it would have to be 92 2s, 2 plus 2 plus 2, or 2 times 92. Plus 3 times 40. Keep on going.
4 times 22.
There you go. 4 times
5
22.
times 9.
Thank you.
6 times 5, 7 times 3, 8 times 2.
And then these we can actually leave out because there's nothing there.
12.
And then 12 times 1. Now, what you'll notice is I put a column in Excel that actually does the multiplications for us. So 2 times 92 is 184. 3 times 40 is 120, and so forth and so on and so forth and so on. What are we going to divide that by?
15.
No.
174. That's how many times we flip. That's the adding of all these frequencies. That's how many coin flips we had yesterday. I know it's different than the 189. Why is it different than 189? Because I can't count. Chances are I screwed up going around the room counting your guys when you had your fingers up in the air. It's okay, it's close enough. It should look like this. It should look like this. If I missed a couple here or there, it's not going to change the overriding shape of that. So we have to divide that by the 174, because that's how many trials we actually saw. This is the way you want to do this, because if you try to do it the other way with the tree diagrams, you have to keep track of all those 50% and 25% and 12.5% and 6.25%, and it just gets kind of annoying after a while. This is a much more direct way of getting at what you need to get to. Fair enough? And then we crunch it all out, and I trust you run a calculator, and I trust you can do this. It's going to come out to this 2.97 flips on average. So it takes us about how many flips? It takes us about 3. It takes us about 3. Now I'm developing a quiz in my mind for you guys for next week to actually give you a tree diagram with the branches on it like this so you can work out why it's 3. So that will save you the agony of having to actually draw the damn thing. But you can fill it out and keep track of the results. And of course you can choose to do it or choose not to do it if you don't want to. That's always your choice. But it actually ends up being exactly 3. It's exactly 3. It takes 3 on average. 3. Now you might be looking at this going, how could it be 3 if most of them are 2? If most of them are 2. Well, I offer you this argument. Half the time, right? Half the time it will be 2. Now let's think about why. This is 174, yeah? That's about 180. Just round to the next nicest number. 92 of you were done after 2 flips. That's about half of you, correct? Now think about why. Imagine the tree diagram starting. Just starting. First 2 branches, heads, tails. But you got to flip at least one more time because you have to see each one at least once. Next branches, heads, tails, heads, tails. Now the entire branch is heads, 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 tails, tails, heads, tails, tails. Half of you are done right there because half of those results you saw each one time. Heads, tails, and tails, heads. So 50% of the time, you're done after 2. Fair so far? Fair so far. 50% of the time, you're done after 2. Much the same way as we were done back here after 2, 50% of the time. The difference between this one and the one we just did was, this one capped out at 3, yeah? This one capped out at 3. So the other half of the time we did 3. On this one, the other half of the time has to happen over here. Now, if 50% of the time we're going to be here, what percent of the time are we going to be here? 25% of the time we're going to be here. 12.5% of the time. Let's call it 12 to make the math easy. It's 12.5, but make it 12. Roughly 6. 3. 1.5-ish. Half of that, half of that, half of that. All of those things added together sum up to 1. That'll be what your quiz is about. The summing of that and making sure that it's equal to 1. So when you add up that 1 with these 2 added together, that's where your 3 comes from. Kind of slick, huh? Because logically you want it to be the same as the other, which would be 2.5. Half the time you're done at 2. Half the time it takes more than 2. The key is it takes more than 2 half the time. That could be 4, 5, 6, 7, 8, 9, or 10. Whereas the previous one stops at 3. You can't go higher than 3. Make sense? Ish? Like I said, I'll have a quiz on this one if you want to do it next week to kind of explore. I want you to explore the tail of this curve because it's pretty cool. Shelby, go, please.
I don't know, this may be so off the charts.
I hope it is. Go.
So when I'm looking at the graph, I can
Yeah,
think
you
about
are.
statistics,
Good.
like the median number.
Mm-hmm.
Can you figure it out that way without having to look at your data?
You can, but the median is less computational than the average.
Okay.
Shelby's asking about something called the median, which I love, and I hope we have time if we tend to get into that with you
Okay.
guys. If not, we'll get into 243, which I think only 3 or 4 of you are taking. the median versus the average. The median number in this case is probably a better one to look at because the distribution is so skewed. Yeah, the average is 3, which puts it over here. Here's how I want you to think about it. We talked about the average being the sharing equally of the data. So how many flips would it take if we took all 516 flips, which is what it took? There were 174 experiments done, which took 516 total flips to do. When you divide that by that, you get 3. So in other words, we're going to pretend that Michael's 12 didn't exist, Trey's 9 didn't. Oh, your 9 didn't get counted for some reason. I don't know why, Trey.
That's okay.
That's all right. It's all good. It wouldn't change it that much anyway.
No.
But you didn't count. The 8 didn't count. Those 2. Everybody flipped 3. All of these 2s didn't really flip 2s. They really flipped 3. That's a little misleading, right? Because half of the people flipped 2. I think that should kind of be in there somewhere, right? So that's the idea of a median versus an average. A median will pull back to where more of the majority of the data live versus just where the true average is. Think of the median as the literal halfway point from low to high, and think of the average as where, if this was a plate of cookies a waiter had to carry, cookies probably better than cocktails because you can't stack cocktail glasses like this. But if this was a plate of cookies stacked high, where would the waiter have to put his or her hand to balance them? If you put it here, it would fall down because of the tail over there. You have to move your hand a little bit that way to balance it. And so that's what the average does. It balances. It equal shares out. I'm not saying it's always the best measure, but that is what the average always is. Fair?
Yeah.
Good. Let's take our 5. I want to come back and play with cards next, and then play with dice, and then give you guys a program that'll let you do any number of sides you want, like an iPod Shuffle, for example. Let's take 5 though.